In this video, we're going to be learning about Hess's law, which is a tool that we can use to calculate the delta H of a chemical reaction by breaking down that chemical reaction into multiple simpler steps. These multiple steps that eventually add together in order to give us our overall reaction back are what we call elementary processes. Now we can see that our elementary processes add together because what we can do is we can take all of the reactants from the two elementary processes and all of the products and combine them together to show that the two produce the overall reaction. So if we look at our reactants here, we see that hydrochloric acid and sodium hydrogen carbonate are the same as the reactants up here, and likewise, if we look at all of our product molecules, we can see sodium chloride, water, and carbon dioxide match the products that we see here. The question is, what do we do with carbonic acid that doesn't appear in the overall reaction? Well, we see that carbonic acid is a product in one step and then becomes a reactant in the next step. Now, if you think about this like math, what do you do with numbers that appear in both the numerator of a fraction and the denominator of a fraction? Well, we know that those numbers cancel and those together would simply equal 1. So what we can do in chemistry is the same thing. If a compound appears on both sides of the reaction, we can actually cancel that compound here because H2CO3, carbonic acid, is immediately consumed in the next step and breaks down into carbon dioxide and water. And then if we add these two together, we see that we get our overall reaction. Now, this process does not just apply with the matter component of a reaction, it also applies to the energy component as well. If we add the chemicals in both equations together, we also need to add the energy term as well. And if we add the two delta H values from each of our elementary processes together, that allows us to calculate the total delta H value of the reaction. Let me explain this in a different way that is more easy to visualize. If we consider this thought experiment of two hikers taking alternate paths through the mountain, hiker A takes a more direct route that happens to be steeper, while hiker B takes a more circuitous and longer route, even if that route has a more gradual climb. Which of these two hikers used more energy in order to get to the apex of the mountain? Well, for those of you that visualize potential energy in terms of gravity, both of the hikers end at the same point away from their starting point, and it technically doesn't matter which route they take. Both hikers would expend the same amount of energy getting there. This compares well to Hess's law because as long as the reactants and products of the elementary processes combine together correctly to give us the overall reaction, it doesn't actually matter what order or which particular steps are used in order to give us the overall reaction. As long as we get there to the same point, the energy consumed or the energy released is going to be the same either way. So in practice, how do we use Hess's law to determine an overall reaction's delta H? Well, if we take a look at these two examples here, we can see how to do this. So remember, the goal is to get our elementary processes to equal the overall reaction here. So if we look at step 2 for the sake of argument, we see that step 2 has two sulfur trioxide molecules just like our overall reaction, which means that this we can simply leave as is. If we look at our first elementary process, however, we see that there are two sulfur atoms and only one in the elementary process. But we can fix that by multiplying this step by 2. So if we do that, we would have two sulfur atoms plus two oxygen atoms as the reactants in step 1, and we're going to add 2 sulfur dioxide and one additional oxygen molecule from the second step, and then our products, if we combine them together, are 2 sulfur dioxide gas from the first step and 2 sulfur trioxide from the second step. Now, if we look to simplify, we see that we have 3 oxygen gas molecules here, 2 from the first step and 1 from the second step, and we see that sulfur dioxide appears as a product and as a reactant, so it can cancel. And if we look at what we have left over, 2 sulfur, 3 oxygen gas, 2 sulfur trioxide gives us exactly our overall reaction here. However, according to the laws of conservation of mass and energy, whatever multipliers we add to each of the elementary processes, we also need to add that to delta H. So for example, if we doubled the quantities of step 1, delta H must also be doubled as well. So we can calculate the overall delta H of this reaction by taking negative 296 kilojoules per mole, multiplying that by 2, and adding it to the delta H of the second step, negative 198.2 kilojoules per mole, and that, if you put into your calculator, should come to exactly negative 790.2 kilojoules per mole. In the second reaction that we've listed, the modification we need to make is a little bit different. So if we look at step 1, we see that we have xenon difluoride, this weird xenon halogen compound here. We see that it's a product in this elementary process, but it's actually a reactant in the overall reaction here. So what we need to do is we need to flip the equation around like this and take xenon difluoride and turn it into a reactant instead of a product. And if we do that, we can see that our reaction works out quite nicely. So xenon difluoride is our reactant compound, and then that means we can add it to the reactants of the second step, xenon gas, and 2 molecules of fluorine gas. And then if we combine our products together, we have, again, xenon gas and 1 molecule of fluorine gas from the first step when we flipped it, and xenon tetrafluoride, the product that we want. We see here, let's cancel xenon because it appears in both sides of the reaction, and let's cancel 1 of the fluorine gas molecules here, and we see our overall xenon difluoride matches with our reactant, 1 fluorine gas, and xenon tetrafluoride. We see that flipping the first reaction allows us to get our overall. Now, if we flipped the direction of our reaction, that means that we must also reverse the direction of delta H. Now remember how delta H works, that if you take an exothermic reaction and have it go backward, delta H stays constant, but the sign changes. So if we want to reverse this negative number and make it positive, we can simply multiply it by -1 in order to turn this negative delta H into a positive number to show that this exothermic reaction, when done backwards, is endothermic with the same magnitude. So if we add these numbers together, negative 262 kilojoules per mole plus 123 kilojoules per mole, and if you do some simple arithmetic or put it into your calculator, you'll find that you come up with negative 139 kilojoules per mole. And that is Hess's law in a nutshell. In short, your goal is to modify the elementary processes so that they add together in order to give you your overall reaction, but remembering that whatever you do to the elementary processes, you also need to do to delta H.